Sketch the graph of f of x equals 3x over x squared minus 1. This function could be described as a rational function. The most basic definition of a rational function is that it is a ratio of polynomials. It's a fraction with a polynomial in the numerator and denominator. In this video, I'll present 4 steps that can be used to graph rational functions, and then we'll apply those 4 steps in graphing f of x equals 3x over x squared minus 1. The 4 steps to sketch the graph of a rational function are: first, identify all asymptotes. Vertical, horizontal, and slant are the 3 kinds of asymptotes that a rational function might have. The first step is to identify those. Then, find the first derivative. The first derivative will give information about where the graph is increasing and decreasing. Then, find a second derivative. The second derivative will give a lot of information about the graph's concavity. And once you have those 3 pieces, asymptotes, information about where the graph is increasing and decreasing, and the graph's concavity, you can then sketch the graph based on the results of those 3 steps. Let's apply these 4 steps and graph f of x equals 3x over x squared minus 1. To begin the process of graphing this function, we'll first identify all asymptotes. Rational functions could have 3 types of asymptotes: vertical, horizontal, or slant asymptotes. Slant asymptotes are sometimes known as oblique asymptotes. In the description of this video, I have links to a more detailed description of the steps required to find all of these asymptotes. For this function, I'll briefly discuss how to identify first vertical asymptotes. Vertical asymptotes occur at x values where the denominator is 0 of the rational function, but not the numerator. If I set the denominator x squared minus 1 equal to 0, I'll find x values that are potential vertical asymptotes. X squared minus 1 equals 0 is a quadratic equation, so it could have up to 2 solutions, and it can be solved by isolating x squared and then introducing a square root to both sides of the equation, including a plus or minus in front of the square root of the number 1. X equals positive or negative 1. If you substitute a 1 into the numerator, we do not get a 0. If you substitute a negative 1 into the numerator, you do not get a 0. That's important because if the result of setting the denominator equal to 0 would give you an x value that also makes the numerator 0, that would be an x value that is not a vertical asymptote. But in this case, x equals 1 and x equals negative 1 will be vertical asymptotes in the graph of this function. Horizontal asymptotes. Horizontal asymptotes are really a description of what is happening to the graph as it approaches negative infinity and positive infinity, as it goes off to the left and to the right. And it's based on the degree of the variable in the numerator and denominator of the rational function. If the degree in the denominator is greater than the degree in the numerator, which is the case in this function, there is always a horizontal asymptote at y equals 0. Basically, what this means is that the graph, as the x approaches negative infinity, the graph will be approaching the horizontal line y equals 0, and as the graph approaches x equals positive infinity, the graph will also be approaching y equals 0. This occurs again every time the degree of the denominator is greater than the degree of the numerator. Slant asymptotes are asymptotes that occur somewhat rarely in rational functions, or I should say they occur in one specific situation. Slant asymptotes occur in rational functions when the degree, again it's based on the degree of the numerator and denominator. Slant asymptotes occur when the degree of the numerator is exactly 1 greater than the degree of the denominator. In this case, the degree of the numerator is not 1 greater than the degree of the denominator. In this case, the degree of the denominator is actually larger, so there are no vertical or slant asymptotes in this function. Now that we've identified all asymptotes, vertical, x equals 1 and x equals -1, horizontal, y equals 0, and no slant asymptotes, we can move on to step 2. Step 2 requires calculus. We're going to find the first derivative of this function, and the first derivative will give a lot of information about where the graph is increasing and decreasing. Rational functions are fractions, they're ratios of polynomials, so to find the derivative we're going to have to use the quotient rule. A review of the quotient rule is on the screen now. The derivative of a quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the original denominator squared. So here the numerator is 3x and the denominator is x squared minus 1. So the derivative will be the denominator unchanged, x squared minus 1 times the derivative of the numerator. The derivative of 3x is 3 minus the numerator unchanged times the derivative of the denominator. The derivative of x squared minus 1 is 2x. So this is the derivative. We'll simplify it a little bit by distributing the 3 before the minus sign. 3 times x squared is 3x squared, and 3 times -1 is -3. And the product of 3x and 2x is 6x squared. There are two like terms that can be combined. 3x squared minus 6x squared is -3x squared minus 3. And in this numerator, there's a common factor of 3. In fact, I'll factor a -3 out to the front and state this first derivative as -3 times the quantity of x squared plus 1 all over x squared minus 1 squared. This is the first derivative of the original function. It's a lot of information this first derivative can tell us. First, critical numbers are places where the first derivative is 0 and where the first derivative doesn't exist. When it comes to rational functions, the first derivative is 0 when the numerator is 0. So in this case, that would occur when -3 times the quantity of x squared plus 1 is equal to 0. But in this case, if I set this numerator equal to 0, I would have x squared equals -1. You can divide both sides by -3 and then subtract 1 from both sides of the equation. When you introduce a square root into the equation, though, to isolate x, you end up with the square root of -1, which is an imaginary number. No critical numbers come from setting this first derivative equal to 0. There are, however, two values where the derivative doesn't exist. The derivative would not exist if the denominator is 0. And remember, we set this denominator, x squared minus 1, equal to 0 whenever we were finding the vertical asymptotes. X equals 1 and x equals -1 are considered critical numbers. Critical numbers are places where the function could possibly change from increasing to decreasing or decreasing to increasing. So I'm going to consider 1 and -1 as the only two critical numbers, and then use those two critical numbers to find intervals on which the function is increasing and decreasing. To do this, I'll set up a number line, and this number line will represent x values in the domain of f of x, and the critical numbers are going to break that domain into intervals. Since the two critical numbers are -1 and +1, there's an interval from -infinity until -1, an interval from -1 to 1, and an interval from 1 to infinity. I'll choose an x value in each interval and then substitute it into the first derivative. Between -infinity and -1, I chose -2. Between -1 and 1, the easiest number to work with would certainly be 0. And from 1 to infinity, I'll choose an integer 2. Substituting this into the first derivative, it's not important what the actual value is, only if it's positive or negative. Because substituting a value in the interval between -infinity and -1, like -2, into the first derivative, if you get a positive number, that indicates that the function is increasing over the entire interval. And if you get a negative number, that indicates that the function would be decreasing over the entire interval. It's not important what f prime of -2 is exactly. It's just important if it's positive or negative. And in this case, if you substitute a negative 2 for x, you'll get a negative value, which indicates that the function would be decreasing from left to right, going down from left to right. Substituting a 0 in for x also yields a negative. It's decreasing from negative infinity to negative 1 and also negative 1 to 1. These critical numbers are places where possibly the graph could change from increasing to decreasing or decreasing to increasing. Doesn't have to change. Additionally, substituting a 2 into the first derivative also yields a negative. This function is actually decreasing over its entire domain. So what I'll do is I'm going to indicate that it's not increasing at all. There are not any intervals where the function is increasing. It's decreasing actually over 3 intervals. It's decreasing from negative infinity to negative 1. Then it decreases again from negative 1 to positive 1 and continues decreasing from 1 to infinity. This does not mean that it decreases from negative infinity to infinity without any breaks in the graph. We'll see that the vertical asymptotes break the graph apart into 3 pieces, and each of those 3 pieces will be decreasing. Extrema are relative max and relative min values, and this function does not have any. Extrema would be points where the graph changes from increasing to decreasing, like this. This would be a relative max value, and a relative min value would be a point where the graph changes from decreasing to increasing, like this. This would be a relative min. This function does not have any of those. There are not any points, there are not any x, y points that would show up on this graph where it changes from increasing to decreasing or decreasing to increasing, so we're saying that there are no extrema in this function. Now that we know the intervals on which the graph is increasing and decreasing, let's move on to step 3, which discusses concavity. And to find information about the graph's concavity, we have to find the second derivative. So there's more calculus in this step. We found that the first derivative was negative 3 times the quantity of x squared plus 1 all over x squared minus 1 squared. To find the second derivative, we'll take the derivative of the first derivative, again using the quotient rule. This time the numerator is negative 3 times x squared plus 1, and the denominator is x squared minus 1 squared. Now, because we factored a constant out to the front after we found the first derivative, by the constant multiple rule, when we find the second derivative, we can just leave that negative 3 in the front of the second derivative till the very end. That will make our problem a little simpler. So when we find this first derivative, or the second derivative with the quotient rule, again, we'll just leave that negative 3 in the front and apply the quotient rule, which says we have the denominator unchanged, x squared minus 1 squared unchanged, times the derivative of the numerator. And the derivative of x squared plus 1 is 2x. Then there's a minus sign. And after the minus sign, we have the numerator unchanged, which is just x squared plus 1. Remember, the constant negative 3 is in front. We're not going to have to worry about that until we state our final answer for final simplified version of the second derivative. So the numerator unchanged is x squared plus 1. The derivative of the denominator requires the chain rule. We have a quantity squared here. So what we'll do is we'll move the power of 2 to the front of x squared minus 1, decrease the power by 1, but then chain along, multiply at the end, the derivative of x squared minus 1, which is 2x. So the second derivative, a little bit more complicated, at least at this point, than the first derivative. We have a lot of simplifying to do. The first step in that simplification, I'll take before the minus sign. There's 2 terms in the numerator, and in the first term before the minus sign, I'll just take the 2x and move it out to the front. And in the second term after the minus sign, I'll multiply 2 and 2x to get 4x, and write that before the quantity x plus 1 and x squared plus 1 and x squared minus 1. In the denominator squared, I had x squared minus 1 squared and then squared that. I'll be multiplying these exponents to get x squared minus 1 to the 4th. continuing this simplification process of the second derivative is something that will always happen when taking the second derivative of rational functions. In the denominator, I have a quantity to the fourth power. This x squared minus 1 to the fourth, this quantity will match up with a quantity of x squared minus 1 in both terms in the numerator. Before the minus sign, there's x squared minus 1 to the second power, and after the minus sign, there's x squared minus 1 to the first power. This can be simplified with the x squared minus 1 to the fourth power that's in the denominator. What I'll do is I'll cancel all three of these out. I'll be dividing the numerator and denominator by x squared minus 1 to the first, which means the denominator will go to the third power. The x squared minus 1 to the first power after the minus sign will be eliminated completely, and the x squared minus 1 to the second power in the first term of the numerator will go down to the first power. That makes things a little simpler. Only have a couple more steps to simplify this second derivative. I'll distribute 2x. Make sure you distribute negative 4x. And that yields 2x to the third minus 2x minus 4x to the third minus 4x. Again, you're distributing negative 4x, so both of the last two terms are negative in this case. I have some like terms here, 2x to the third minus 4x to the third, and negative 2x and negative 4x, and that yields negative 2x to the third minus 6x all over, x squared minus 1 to the third. Next, I'll factor negative 2 out to the front, negative 2x actually, out to the front of the numerator. And when you factor that negative 2x out to the front, you're left with x squared plus 3 in the parentheses. And the last step in this simplification process will be to multiply the negative 3 by the negative 2x that you've factored out to the front of the numerator, and that gives the simplified version of the second derivative. Positive 6x, negative 3 times negative 2x is positive 6x times x squared plus 3 over x squared minus 1 to the third. Now that you have the second derivative, you can determine some information about the graph's concavity. Finding information about the graph's concavity very much mirrors the process used to find information about where the graph increased and decreased. Information about the graph's concavity comes from the second derivative, including first finding possible points of inflection. Possible points of inflection come from x values where the numerator is 0. In this second derivative, we have the numerator factored as 6x times x squared plus 3. So possible points of inflection will be places where each of those factors are equal to 0. So x equals 0 is one possible point of inflection, and x squared plus 3, if it had a solution, would also be places where the graph could change concavity. But in this case, setting x equal to 0 yields two imaginary numbers, plus or minus the square root of negative 3. Since those are imaginary, those are not possible points of inflection. We only have one. X equals 0 is a place where there could be a point where the graph changes concavity from concave up to concave down, or concave down to concave up. Other x values where the graph could change inflection are places where the second derivative doesn't exist, which are, again, the two places where there are vertical asymptotes, x equals 1 and x equals negative 1. These would not be points of inflection. There would not be any points at the x values of 1 and negative 1, because those are vertical asymptotes, but the graph could change concavity from one side of a vertical asymptote to the other. So when I determine intervals of concavity, I'm going to include x equals 1 and x equals negative 1, as well as the possible point of inflection, x equals 0, that I have found earlier. So I'm going to again make a number line, and this number line will include negative 1, 0, and 1. It breaks the domain of the function apart into, this time, 4 intervals. An interval from negative infinity to negative 1, an interval from 1 to infinity, negative 1 to 0, 0 to 1, and 1 to infinity. And again, mirroring the process that I used when determining where the graph was increasing and decreasing. I will choose a value in each interval, substitute it into the second derivative. So right now, I am choosing a value in each interval. Going to have to choose a fraction in the interval between -1 and 0 and 1. And then from 1 to infinity, I'll choose an integer like 2. And again, I'm only concerned with whether this yields a positive or negative in the second derivative. It's not really important whether I get what the actual value is. If it's positive, I know that every x value in that interval will be concave up. If it's negative, I'll know that every value is concave down. So I just want to know whether I'm finding and getting a negative or a positive number for x equals -2, and substituting x equals -2 into this second derivative will yield a negative number. So that means that the graph of the function will be concave down from -infinity to -1. Substituting a -1/2 in for x yields a positive number. It doesn't matter what that number is, but if you would substitute a -1/2 into this second derivative, -1/2 squared is technically 1/4, but then 1/4 minus 1 would be negative, and when you raised it to the third power, it would still be negative. -1/2 squared is positive, plus 3 is positive. Again, doesn't really matter what it is, but just that this factor is positive, and 6 times -1/2 would be negative as well. So in the three factors of the second derivative, you would have a negative times a positive in the numerator, a negative, divided by a negative, which is positive. Because I'm only concerned with whether it's positive or negative, I don't need to know what that actual positive value is. Knowing that it's just positive tells me that the function would be concave up from -1 to 0. When I substitute a positive 1/2 for x, I would still have a negative value in the denominator, but the numerator would include two positive factors. Two positives in the numerator, one negative in the denominator, means that f prime prime, the second derivative evaluated at 1/2, is negative. This function is concave down from 0 to 1. Substituting a 2 into the second derivative would yield a positive number. This function is concave up from 1 to infinity. Using this information, I can state that this function will be concave up on the open interval from -1 to 0, and also from 1 to infinity. And this is just summarizing what I got on the number line. This function will be concave down from -infinity until -1, and then it's also concave down from 0 to 1. Now there is one point of inflection. A point of inflection is a point where the graph changes concavity. This function did change concavity before and after -1 and before and after x equals +1, but those are vertical asymptotes. Those will not be points of inflection. X equals 0, remember, when we found our points of inflection, we found that x equals 0 was a possible point of inflection. And taking a look at the number line, it does turn out that the graph changed concavity before and after 0. It was concave up before 0, and it's concave down after 0. So x equals 0 is a point of inflection. And what I'm going to do is I'm going to write an ordered pair here that will be a point on the graph. When x equals 0, if I evaluate f of 0, I'm substituting a 0 into the original function to find the y-coordinate of a point on the graph. When the x-coordinate is 0, f of 0 would be 3 times 0 over 0 minus 1, 0 over -1. 0 divided by anything is 0. So there is a point of inflection on the graph at 0, 0. Now that I know all of the intervals where the graph is increasing and decreasing, I know all of the intervals of concavity, and I even have an additional point of inflection, I have enough information to draw the graph. And that's what I'll do in step 4. Steps 1, 2, and 3 provided us with a lot of information about the graph of this curve. We know the vertical asymptotes, horizontal asymptotes, where the function is increasing and decreasing, and all about its concavity. When drawing the graph, the first thing that I'm going to do is represent the asymptotes with dotted lines. And the asymptotes certainly aren't part of the actual graph of the function, but they form a boundary for the graph. The vertical asymptotes are vertical lines that the function will never touch. This function will never get to x equals -1 and x equals 1. The horizontal asymptote is a little different. The horizontal asymptote, as I mentioned earlier, just provide a border or a boundary for what the graph is going to approach as x approaches -infinity and as x approaches +infinity. I drew dotted lines just going off to the left and right on my coordinate plane here because the curve could go through the horizontal line y equals 0 in the middle of the graph, but as it goes off to the left to -infinity, it'll get closer and closer to this horizontal line, as it goes off to the right to +infinity, it will be getting closer and closer to y equals 0. The next thing I'll do is I would plot the relative maxes or mins if there were any, but there's not. And I'm going to plot the points of inflection, which there is one. There's a point of inflection at 0, 0. So I really only have plotted one point. Most of my sketch of this curve will be based on where the graph is increasing and decreasing and where it's concave up and concave down. As I look at the domain of this function from left to right, the first interval I see is from -infinity to -1. This function is decreasing from -infinity to -1, and it is concave down from -infinity to -1. So in this interval of the curve, I'm going to be drawing a curve that's decreasing and concave down. The section of the curve will look something like this, what I've drawn above the coordinate plane. In this interval, it'll be decreasing and concave down. And the only place that I could draw a curve that is bounded by the asymptotes that I have is down kind of in the fourth quadrant. I'm going to do my best to draw a curve that is decreasing and concave down, that is getting closer and closer to y equals 0 as it goes off to x equals -infinity, and it gets closer and closer to the vertical line x equals -1 as it approaches -1 from the left. If I had to draw a very accurate graph, I could perhaps evaluate f of -2 and f of -3 to get actual points that this curve goes through. I've done an estimate on the screen here, which a lot of times is sufficient, but if I wanted to draw a very, very accurate graph, I could plot a couple more points. I've only plotted 0, 0, but that's enough to give a general sketch of the function. The next interval that I see from left to right goes from -1 to 0. From -1 to 0. Goes from the vertical asymptote at x equals -1 to the point of inflection at 0, 0. This curve is decreasing from -1 to 0. Certainly it's decreasing throughout its entire domain. It's decreasing from -1 to 0. And how about its concavity? Well, I'll circle this on the screen now. It's concave up from -1 to 0. So above the coordinate plane, right above that interval, I'm going to draw a curve that is decreasing and concave up. Decreasing concave up curve has this general shape. It's going down from left to right, but it's concave up. It's going to end, this interval ends at the point 0, 0, and it begins at the vertical asymptote x equals -1. So the way that a decreasing concave up curve could fit in that interval would look like this. This is a curve that's decreasing and concave up, ends at the point 0, 0. The next interval goes from 0 to 1. The next interval goes from 0 to 1. The curve is still going to be decreasing, but look at its concavity. It's now concave down from 0 to 1. So a curve that is decreasing and concave down will look just like the first interval that I dealt with, -infinity to -1. From 0 to 1, the curve will also be decreasing and concave down. Now it's going to start at that point 0, 0, and in this case it's going to be approaching a vertical asymptote at x equals 1. So I'll do my best to draw a smooth curve that is decreasing and concave down, beginning at 0, 0, getting closer and closer to the vertical line, x equals 1. Finally, the last interval, which goes from x equals 1 to infinity, is going to be decreasing again. This function was decreasing over its entire domain, and it's concave up. A curve that is decreasing and concave up, look above the coordinate plane at this interval. Decreasing concave up looks like this, going down from left to right, but concave up, bounded by the vertical asymptote at x equals 1, and the horizontal asymptote, the limit at infinity, it's getting closer and closer to y equals 0 as it approaches infinity. And so what I have on the screen now is the general shape of the graph of f of x equals 3x over x squared minus 1. It's decreasing, concave down from negative infinity to negative 1, decreasing concave up until it gets to 0 from negative 1, decreasing concave down from 0 to positive 1, and then ends from 1 to infinity, decreasing and concave up. These 4 steps can be used to sketch the graph of any rational function. The steps again: vertical asymptotes, use the first derivative to find where the function is increasing and decreasing, and use the second derivative to determine concavity.